Hello, so we have a problem where we have three gases in a Stefan tube. We have acetone, methanol, and air, and we want to plot the mole fractions as they go up the tube. So we're going to do some numerical calculations, some scientific calculations, integrations, initial value problems, and we're going to make plots. So we're going to import numpy as np, and then we're going to have to bring in an IVP solver. So we're going to use scipy.integrate and import solve underscore IVP. And then we're going to have to find a root, because we're going to find the values when the mole fractions of acetone and methanol are at 0 at the very top, where air is flowing in excess. And then we're going to have to make a plot of this, so we're going to use plotly subplots and a scatter plot, so we're going to use graph objects, and then we're going to change the background color to dark, so we're going to import plotly.io and change the theme to plotly dark. Alright, so that we have constants and things that we found by scaling. So we have D12, D13, and D23, and they are all in meters squared per second. We have our pressure in pascals, our temperature in Kelvin, our ideal constant in joules per mole times Kelvin, and then we can use all of that stuff above to find the concentration. And then this delta is the total length of the tube in meters. And then we can use our scaling to find F12, F13, and F23. We're going to have, and then from our scaling, we found that N1i and N2i are about 10 to the minus 3 magnitude. And then we have given our mole fractions of acetone and methanol at the interface, Y1i being acetone and Y2i being methanol. Alright, so we're going to want to use our IVP solver. So for that, we're going to need a function, a time span or a span over that we want to look at. We're going to need our initial values. Our method, it defaults to RK45, but we're going to change it to radal. And then we're going to change our dense output to true, because we want to have that dense output to put into a variable. That way we can work with it. So first we need a function, but first we need to change our variables. So we have our equations, we have everything except our N1 and N2. We don't know those yet, but we have our initial guesses. So we're going to set our N1 equal to our guess and our N2 equal to our guess. Alright, and then we're going to define our function. We're just going to call it dy like they do in the book. Define dy, and we're going to use it with our independent first and our dependent second. And we're going to call our y's. So y1 is just going to equal the first in the iteration. Y2 is going to equal the second. And y3 will just be the difference of 1 and the previous 2. y3 equals 1. Alright, so then we're going to return an array which we can use to do our calculations. We're going to have y1 times n2 minus y2 times n1 divided by f12 minus y3 times n1 divided by f13. Now we have y2 time, or we need a parenthesis there because it's just one thing, divided by f12. So y2 times n1 y1 times 2 divided by f12 minus y3 times n2 divided by f23. Alright, so then we're going to want to see what we get. So we're going to do our solve IVP with our function dy, a span from 0 to 1. Our initial values y1i and y2i. Our method, which we already chose to be radout. And set dense output equal to true. Oh, let me take that out so we can actually see what we get. So we get in sol. Oh, we need to put dense output. There we go. We get in sol, we get this. So we're going to look and see what we get. Res.sol. We're going to see what we get at 1. Oh, we gotta set our that equal to the variable res. That way we can actually get something out. There we go. So we get an array. It doesn't make sense because they should be at 0, but that just means our initial guesses are wrong, which we already knew in the first place. We were just doing a magnitude guess. So we need to do some root finding. So if we look at the root function, we need a function and our initial inputs. So what we're going to do is we're just going to have some new function. We're just going to call it f. So we're going to define some function f with n as its parameter. Alright, so then we're going to have n1 equal to the initial value, the first value, and n2 equal to the second value. Alright, and then we're just gonna take, we're just gonna do this equation again. So we're gonna define dy with eta and y. And we'll just copy this. I can probably just do all of this. There we go. I just need to do that. And where is that? Unindent does not match unindent. Let's just redo that. I obviously messed up somewhere. Control C, Control V. We're just gonna have all that. Oh. Okay, I did that wrong again. Let's try that again. Oh, so these have to be indented. There we go. Okay, so we get some. So if we just do this, we're going to get our IVP solved again. So we're just going to store that and see what we get at 1 again. But it shouldn't change at all because we didn't really change anything. Yep, we just get the same exact thing because we didn't actually find the roots. So now we have to actually find the root. So we're just going to return this. Return res.sol. Let's do that backwards. Res.sol is outside the function. Let me just put that in there. There we go. Okay, so now we need to find our root. So let's do root of f with our initial values n1i and n2i. Okay, so we get a message that the solution converged, and we have this array here in X. These are our N values. This is for acetone here. This first one's for acetone, and the second one is for methanol. So we can put that in. We found our fluxes for acetone and methanol, so we can just put those in. So here we're just going to, we'll just copy this up here. And we'll just say this is the result. And oh wait, no. Let's just make a new one. No harm in it. So we'll just say our result is equal to that. Our N1 is equal to N, and it's going to be res.sol, or res.x, sorry, res.x. The first one, and N2 is going to be the second one. Alright. And then we just take this again. To solve. So then we get the solved initial value problem here. We're going to store that. And we're going to see what we get at 1. Res.sol at 1. So very, very small, which is exactly what we were looking for. Res.sol. And if we do 0, we should get our initial values, which is good. So now we have all of our let's just check. You can see here we have this would be our array here. So res equals sol. Alright, so let's just get rid of that again. Alright, so now we want to take all of the values that we found and put them into a plot. So we're just going to make some new thing, eta, as we're plotting, but we want it to be, we want equal spaces on eta. So we're going to use numpy again to do its linear spacing. Start at 0, end at 1. And we're going to do 51 numbers just to make it even. So let's just check that again. See what that makes sense. Yes, that makes sense. Okay, good. Perfect. So now we need all of our numbers from our solution up here. So we're going to res.sol, and we're going to do it for the values of eta plot, and we get this big array. So these first values here, these would be the values for acetone, and then these ones down here would be the values for methanol. So we want to plot it for acetone, methanol, and air. We will get to the air in a second. So now we just need to put it all together into a plot. So we're just going to go up here, since we already checked that. Looks good. We're going to just make a new solution. Why not? It's going to be res.sol of eta plot. Alright, that way we can call back to it easily. Alright, so now we are going to make a plot, make some traces. So we're just going to have it labeled as our figure. So our figure is just going to be make subplots, make underscore subplots, if I can spell right, subplots. Alright, so now we need rows. Rows is just going to be equal to 1. We need columns. That's going to be equal to 1 as well. And that's it for the figure. Now, that's it for that. So now we need to make adjustments. We need to actually put our plots on the put our lines on the plot. So we're gonna do we're gonna take our figure and we're gonna add some traces. Add trace. So we're gonna use our go, our graphical objects, and we're gonna make a scatter plot, right? So x is going to be equal to, our x values for the plot is just going to be the eta plot, right? Our eta plot, and then we're going to have our y is just going to be equal to sol. So we have our solution, right? So if I were to go here, let's add some code here. So if we were just to write sol, this is our array. So we want the first object in the array to be acetone, and this is acetone. So what we're going to do is just make y equal to sol, the first element in sol, and then we're going to name it. We're going to name it acetone. Right? Okay, and so then we need to do the same thing for methanol. So we're just going to copy that, paste it, change that variable, and change the name to methanol. Alright, so now we need to do make a trace for air. So to do this, I'll just go ahead and change this to air before I forget. Air. So basically, we're going to be doing all of these values. So the mole fraction of air is just going to be equal to 1 minus the value of acetone minus the value of methanol. And so to do that, we're just going to just do 1 minus, we're going to be sol of 1, or 0, to subtract the acetone, and then we're going to subtract the methanol, and then we're going to run this, and we are going to get our plot, which is really long, but if I were to close it a little bit, it looks better. So we finally have our plot, and this shows you that methanol starts at a higher mole fraction, and as it goes all the way to the top, this is eta adjusted. This is our scaled eta. So if we wanted to do it for the actual length, we can just multiply it by the total length, or we'll just call it delta since we can. Delta times delta times delta. There we go. And so now we have it in terms of the total length of the tube. So this is showing you, so this is the very bottom of the tube where the methanol and acetone start, and this is the very top where the mole fractions go to 0, and it's just completely air at the top.